Good morning, students. Today we'll start section 4. Our first topic is principal directions, principal curvatures, and equation for principal curvatures. So firstly, let us define what are principal directions. Suppose we are given a surface and we have a point P on the surface. Then there can be infinitely many normal sections at this point of the surface, and every normal section at this point will have a curvature which is called normal curvature. Now we will find the direction in which the curvature of the normal section is maximum or minimum. These are also the tangent lines along which this curvature is maximum or minimum. These are the tangent lines at the point P of the surface. So if the curvature of normal section is maximum or minimum along these lines, then these are called principal directions. So we define what are principal sections. The normal sections at a point on the surface having maximum or minimum curvature, those sections are called principal sections, and the tangent lines to which the curvatures are maximum or minimum, those are called principal directions. The curvature of principal sections, those are called principal curvatures. Now there are two principal curvatures. One will be corresponding to the maximum value of curvature and the second will be corresponding to the minimum value of curvature. So let us find the quadratic equation giving us the two principal curvatures. So our next topic is the equation for principal curvatures. Now the normal curvature kappa n at any point P on the surface in the direction du dv is given by kappa n is equal to L du square plus 2m du dv plus n dv square divided by E du square plus 2f du dv plus g dv square. This formula we have already derived in the section 3. If we take Lm be the direction coefficients in the direction du dv, then the relation between the direction ratios and the direction coefficients is given by Lm is equal to du dv divided by square root of E du square plus 2f du dv plus g dv square. This formula we have already derived in the previous section. Now because by the first fundamental form this expression is ds square, so its square root will become ds. So this quantity will become du by ds and dv by ds. So we get the values of L and M as du by ds and dv by ds. Therefore the value of kappa n from here, that will become L du by ds whole square plus 2m du by ds into dv by ds plus n into dv by ds whole square. Substituting the value, this is L and dv by ds, that is m. So kappa n will become L into L square plus 2m into Lm plus n into m square. Now for the maximum or minimum value of the normal curvature kappa n, we must have its differential coefficient, that must be 0. So differentiating the value of kappa n, we get and equating to 0, so we get the derivative of L square is 2L dl. L will remain as it is, m as it is, and using the product rule between the terms m and L, m as it is, differential coefficient of L is dl, plus L as it is, derivative of m is dm, plus 2n m dm is equal to 0. Dividing throughout by 2, we get the equation LL plus mm into dl plus ml plus nm into dm is equal to 0. Now we know if L and m are the direction coefficients, then they are connected by the relation EL square plus 2FLM plus GM square is equal to 0. Differentiating both sides of this equation, we get E as it is, L square का derivative 2L dl plus 2F is constant. Here by using product rule, M as it is derivative of L is dl plus L as it is derivative of M is dm. Here G as it is derivative of M square, that will be 2M dm is equal to 0. Dividing throughout by 2 and combining the terms with dl and dm, we get the equation. Let us consider this equation as equation number 2. Now multiplying this equation by lambda and adding to the next equation, we get LL plus MM plus lambda into EL plus FM into DL plus ML plus NM plus lambda into FL plus GM into DM is equal to 0. Here the multiplication of second is by lambda, and then we have added. We have multiplied this equation by lambda and added to 1. So we have obtained this equation. Now from here, this further implies that the coefficient of DL that is equated to 0 and the coefficient of DM that is also equated to 0. So we get the equations LL plus MM plus lambda into EL plus FM is equal to 0, and from here ML plus NM plus lambda into FL plus GM is equal to 0. Now multiplying this equation by L and this equation by M and adding, we get the equation L into L square plus 2M into LM plus NM square plus lambda into EL square plus 2FLM plus GM square is equal to 0. Now by definition, this is kappa curvature of normal section and this quantity is 1. So we get kappa n plus lambda is equal to 0. From here we have obtained the value of lambda, which is given by minus kappa n. Now substituting the value of lambda in these two equations, equation 3 and equation 4. If we substitute the value of lambda here, we get the equation LL plus MM minus kappa n into EL plus FM is equal to 0. And the equation 4, after putting the value of lambda, will become ML plus NM minus kappa n into FL plus GM is equal to 0. Now these two equations can again be written by combining the terms in L and M separately. We get the equations L minus E into kappa n into L plus M minus kappa n into F into M is equal to 0. And this equation can be written as M minus kappa n into F into L plus N minus kappa n into G into M is equal to 0. Now eliminating L and M from these two equations, we get the corresponding determinant equated to 0. In the first equation, the coefficient of L is L minus kappa n into E, and the coefficient of small m is M minus kappa n into F. In the second equation, the coefficient of small l, that is M minus kappa n into F, and the coefficient of M, that is N minus kappa n into G. Now this determinant equated to 0 gives us the equation the product of these two terms minus product of these two terms is equal to 0. Multiplying and simplifying this, we get the equation Eg minus F square into kappa n square minus kappa n into En plus Lg minus 2Fm plus Ln minus M square is equal to 0. As we already discussed in the previous chapter that Eg minus F square, this is a quantity H square, and Ln minus M square is denoted by T square. So we get the quadratic equation which gives us the maximum or minimum value of the curvature at the point P of the surface. This equation is quadratic and this equation is having two roots, and the roots of this quadratic equation are called the principal curvatures of the surface at the point P, and we denote these principal curvatures by kappa A and kappa B. Now from this quadratic equation we can find the sum and the product of the roots. Now sum of the roots is given by negative of this coefficient divided by H square, so that will become En plus Gl minus 2Fm divided by H square, and the product of the two principal curvatures, Those are kappa A into kappa B, that is given by the ratio of t square and h square. T square by h square, that gives us the product of two principal curvatures. Now, next we define some important curvatures. The first type of curvature is mean curvature. The sum of the principal curvatures kappa A and kappa B, that is called first curvature at the point P, and it is generally denoted by capital J. So capital J means first curvature, that is the sum of kappa A and kappa B. Next type of curvature, that is mean curvature. Mean curvature is the arithmetic mean of the principal curvatures kappa A and kappa B. Means it is generally denoted by mu. Mu is given by kappa A plus kappa B divided by 2. This is mean curvature. The last type of curvature, that is Gaussian curvature. Gaussian curvature is the product of the principal curvatures kappa A and kappa B. So the product of these two curvatures, that is called Gaussian curvature at the point P of the surface, and it is denoted by the letter capital K. So capital K is equal to kappa A into kappa B, and from here kappa A into kappa B is given by ln minus m square divided by Eg minus f square, because this is t square and this is h square. So we can write Gaussian curvature capital K is equal to t square divided by h square. So these three are important types of curvatures which will be used in the numerical problems later. So this completes your topic, principal directions, principal curvatures and equations of principal curvatures, and some important types of curvatures. Thank you.